Okay, everybody, welcome back. Happy Friday to you. We are going to dive right back into chapter 14. I thought we would finish 14 in the 9 o'clock hour, but then I started on a difficult practice problem, which I told people that I had put on exams before, and suddenly everybody cared and asked lots of questions. So it took a little bit longer than we were expecting. So we'll do our best, and we'll see where we get today. I want to start with something which I think is unexpectedly difficult for you, and that is the concept of a cyclic hemiacetal. We learned last time that nope, that's not it, there we go. For acetal formation, one of the intermediates along the way is this hemiacetal, where there's what used to be the carbonyl carbon that's bonded to an OH group and an OR group. And I mentioned that they're not that stable and they're not the final product. If we remove water, we can push the reaction forward to the acetal. But if we supply an excess of water, normally the hemiacetal falls back apart to the starting materials. One thing we said in your class last time was that hemiacetals are also not stable to bases. A base removes the proton from the OH group, and then a negatively charged oxygen kicks off the OR group. Now, the exception to all of that is that cyclic hemiacetals can be stable, and that's two different, two issues why. One is that rings of a certain size, like 5 and 6 membered rings, are not very strained and can be quite stable. And the second issue is that intramolecular reactions are favorable and fast. In regular acetal formation, you have to have a second molecule of alcohol, or rather in regular acetal formation, when you're making the hemiacetal, the alcohol has to find the carbonyl molecule. They're not attached to each other, and it takes a while for molecules to swim around and find each other in solution. In contrast, when you have in the same molecule an electrophile, that is the electron-poor carbonyl carbon, and here's the carbonyl oxygen, and then a nucleophile in the same atom, in the same molecule, the reaction's faster because the nucleophile doesn't have to wait and swim around to try to find the electrophile. It's already right there. They're tethered together. So let me show you how this reaction happens. I'm going to draw the product for you to begin with. And this is maybe an example that comes out of your text. Now, I've already told you that this is a hemiacetal. However, I've observed in talking to some of you that that's not immediately obvious. And to me, because I've been doing this for 20 years, I'm like, come on kids, what's the problem? But for you, where this is your first time through, you're not used to seeing and being able to focus in on molecules, and you are sometimes easily distracted by irrelevant details. So let me redraw this acetal in a slightly simplified way, hemiacetal rather, in a slightly simplified way, and see whether it makes more sense to you. Is that easier to recognize as a hemiacetal? Okay, why? Because I've abbreviated the stuff that you can ignore. I've told you what you can ignore. You are not confident in your ability to focus in on what's important yet, so you're not sure that you can ignore stuff. Does it matter that these two OR groups are tethered together? Yes and no. I mean, it makes the reaction faster, but in terms of recognizing the functional group, it's sort of irrelevant, okay? The problem I see is that some of you look at that and you say, oh, that's an alcohol. And you're not wrong because there is an OH group, but you're also totally wrong because that's not a typical alcohol functional group. In a typical alcohol functional group, the things attached to the carbon that has the OH on it are either protons or carbons. This is different, and you can see the difference is that the carbon that has the OH group is itself attached to an OR group. All right, that's the structural pattern for hemiacetals. And you need to be aware of that, and you need to be confident enough in that understanding that you can temporarily ignore the fact that the purple group here is connected over there. Okay? Yes?
What's the difference between a hemiacetal and an acetal, just OH-OH versus OH-OR?
OH-OR is hemiacetal, OR-OR is acetal. There is an OH-OH version, that's called the hydrate, but it doesn't involve alcohols at all. We'll maybe get to it later. Okay, good. Others? Okay, the other thing to realize is you can tell by looking at the hemiacetal whether it came from an aldehyde or a ketone. And I'm sorry for all the consonants today. They lost the pop filter on this mic, so hopefully you guys can stand all the... All right, here's the carbonyl carbon. And you look at the two, what used to be the carbonyl carbon, you look at the two things that are attached to it, and that tells you whether it was an aldehyde or ketone. If one's a hydrogen, one's a carbon, it used to be an aldehyde. If both are carbon, it used to be a ketone. All right, let's take you through the mechanism of this so you could get to the point where you can predict this product. I would start by, well, first we'll protonate, as you know, for acetals, we protonate the carbonyl oxygen first to get an oxonium ion intermediate, which is going to look like this. Positively charged oxygen. Then, rather than waiting for some alcohol to come along, the molecule already is embedded with an alcohol in it, and that alcohol will do the attacking, and we'll show that here. Now, anytime you draw an arrow from a nucleophile in a molecule to an electrophile in the same molecule, you are likely proposing to make a ring. That's called an annulation reaction. That comes from the Latin word for ring. You've heard the term annual. Spanish speakers, you've referred to rings as what? Anillos, right? So it's the same basic word. We're making a ring. That's an annulation reaction. That term is going to come up later on in the class, so I thought we'd introduce it now. How can you tell what size ring you're making? Well, start with the nucleophile. That's 1, 2, 3, 4, and then number until you get to the atom that's the electrophile. That's atom 5. So I know here that I had to have made a 5-membered ring. So then just draw a polygon, and I know one of the atoms in that polygon's got to be my oxygen. Okay, and that's the purple one. It should still have its proton on it. In red is the new bond I just made. Then I'm going to number around the ring 1, 2, 3, 4, and 5. Carbon 5 used to be my carbonyl carbon. Attached to carbon 5 is got to be the hydrogen from my aldehyde, and then the pink OH group. All right, and then to make the hemiacetal, I would use the conjugate base of my acid to remove the proton, and that gets me there. All right, again, 1, 2, 3, 4, and 5. Okay, questions about that? It's going to get worse before it gets better because we're going to do some more. Yes?
So it grabs a proton, then it splits.
Are you asking, sorry, about this step? The conjugate base of your acid removes the proton, nothing splits. I'm not sure what I'm seeing, what you're asking.
Do we go from ring to, do we go from string to ring to string?
What we are doing is showing you how you go from what we will call the linear form to the cyclic form. What's drawn here is something I mentioned earlier. This is just an abbreviation of what's here. It's the same thing. Okay, Now let me give you an example starting with, and I've asked questions like this before, starting with, is this how we want to do things? No, that's not how we want to do things. Let's start with, all right, let's start with this molecule. And again, predict what the closed chain form should be if we put this molecule in mild aqueous acid. How you do this is carbonyl carbon, carbonyl oxygen, then identify the nucleophile, which is the OH group. We're not going to draw the mechanism for this. We're simply going to predict the product. If you want to go back and draw the mechanism, that might be useful for you to do. Number from the alcohol to the electrophilic or electron poor carbon. That's 6 atoms, so that tells you that the cyclic hemiacetal has to be a 6-membered ring. So draw a 6-membered ring where one of the oxygens, or one of the vertices of the ring is an oxygen. That's going to be your nucleophile. Then choose a way to number around the ring. At this stage, it doesn't matter whether you go clockwise or counterclockwise. 1, 2, 3, 4, 5, 6. Carbon 6 is your carbonyl carbon. Carbon 6 is got to be bonded to the same stuff that it was bonded to here. The carbonyl oxygen becomes the pink OH group. And then the methyl group on carbon 6 is there. And again, if I started with that cyclic hemiacetal, I could tell that it used to be a ketone by looking at the 2 groups attached to the carbonyl carbon. All right, questions there? Yes?
So you're just assuming like the light purple alcohol group, so just the mild conjugate base to the acid stole that proton?
No. The thing that steals the proton is whatever. So as I said, mild aqueous acid, you're probably looking at H3O plus and its conjugate base water. So probably at this stage of the mechanism, you're asking what does this?
Yeah.
Probably water.
Okay.
Yep.
So it just moves the proton from the light purple.
No. It removes the proton from light purple, and then what that does is that regenerates your acid.
Okay.
The pink OH group comes from the carbonyl carbon. It gets its proton from the acid to begin with, yeah. All right, what else? Uh-huh.
What's the 2 arrows going from the 2 cyclic molecules?
The 2 arrows, this is an equilibrium arrow. This is an intermediate that precedes this one.
Okay.
Yep. Okay. So, as I said, it's going to get worse. There's an example in your text which I think was maybe troubling to some of you. It was something like this, and it gave you an alcohol and then acid, and you were supposed to figure out what to do. And again, some of your ability to deal with these kinds of problems is going to relate to how well you recognize key functional groups. If you just thought that was an alcohol, some of you were thinking, well, maybe I need to do an SN2 reaction or something where I need to replace this OH with this alcohol group. That would be exactly the wrong thing and the wrong mechanism to do, because this is not an alcohol, it's a hemiacetal. And so just as we showed you last time for the acetal formation mechanism, just as a hemiacetal can go on to form an acetal if you supply an alcohol and you remove water, we can do that here. It's no different. The only difference is we've started with the hemiacetal. So starting with a cyclic hemiacetal, this reaction is really, can you complete the acetal? And the way you do that, based on the mechanism we just showed you, is the OH group removes a proton from the acid that converts it into a good leaving group. Then the OR group in the ring becomes the kicker-offer. And that's going to give you the oxonium ion. All right, that's now reactive enough for the OH group to attack the carbonyl carbon to generate this intermediate, and then the conjugate base of our acid will remove a proton to give us the final product, which looks like this. That's now an acetal. How do you recognize it as an acetal? There's the carbonyl carbon, there's the first OR group, and there's the second. And you can tell, even though it's not really, we never even saw the linear aldehyde product, the linear aldehyde starting material, because we started with the hemiacetal. You can tell that this acetal comes from an aldehyde by paying attention to what are the two non-oxygen groups on that blue carbon. Yes?
In the book, when it draws the mechanisms, sometimes when the water leaving group comes off, it just draws one of the arrows as opposed to the O kicking it off. And I'm wondering, is there any truth to that, or is it?
Yeah, so your text will show, I'm glad you mentioned this, your text will show an alternative kicker-offer mechanism. I will draw it for you here, and I will tell you that that option is fully equivalent and indeed indistinguishable from what we might draw above. So what you're saying is, rather than have the purple kicker-offer kick off the pink leaving group, they show the pink leaving group simply leaving, and the resulting intermediate looks like this. What is the relationship between this intermediate and this one that we've drawn down here? They're simply resonance structures. And remember, resonance structures are not isomers, they are not different molecules, they are the same thing that only differ in how you're choosing to draw the electrons. And what they represent is incomplete pictures of the same molecule. So it is totally correct to draw the mechanism this way. It is also totally correct to draw the mechanism this way. In fact, you cannot tell the difference between those two options. I've had students who, on a previous exam, were supposed to select an incorrect step in a mechanism, and they chose this one because they thought, well, that's not exactly the way the book drew it. And I said, this mechanism and this mechanism both lead to the same resonance structures. You cannot tell the difference between the two. They are both correct. So don't make that mistake. But yeah, I understand that that's a little bit difficult, and your text, I think, is somewhat inconsistent on how it shows whether that group leaves or on its own or just gets kicked off. Understand, those are two different views of the same reality. Okay, what else? All right. Now let's do the thing that took us probably 20 minutes to get through in the 9 o'clock hour. People were so scared. Are you ready? I told them, I will tell you what I told them. I feel like a Sith Lord. Your fear gives you strength. Use it to motivate yourself to practice. All right, so I'm going to draw for you a much worse version of a cyclic hemiacetal. And yes, my friends, that is a chair. If you thought that you were never going to see a chair again after 351, you were wrong. So here it is. Now, That molecule is called beta-D-glucopyranose. It's a carbohydrate. You won't need to know the name until later. For right now, it's an example of what we've been talking about. Now, if you're not good at focusing in on the relevant portion of a molecule, you might look at that and say, okay, it's a chair, and there's a lot of OH groups. And you're right, okay? You might say, that's just a lot, I don't even know what to do with that, there's so many OH groups. Well, not all of the OH groups are the same. And if you're just relying on 351 intuition, you would say, well, that's a primary alcohol, and that's different from the rest of these, which are on maybe secondary carbons. And that's true, but that's not the major difference. The major difference is, if we're going to play the Sesame Street, one of these things is not like the other game. It's this one. And the reason it's different is because it's on a carbon that's attached to an OR group. That is the hemiacetal. And in fact, you can tell that that hemiacetal used to be an aldehyde because the blue carbonyl carbon is bonded to a hydrogen and a carbon. All right? So that is a cyclic hemiacetal.
Wait. Why is that the case for the highlighted one and not the other?
Why is that the case for the highlighted one and not this one?
Yeah.
This oxygen is attached to a CH2 group. Yeah, not to another carbon. And I can make that even more obvious by altering my drawing here and just drawing CH2OH, though I actually don't like that, so I'm gonna, sorry, just go back to that. Okay. So, as we've done before, what we did before was going from the linear form to the cyclic form. Now we got to go the other way. What if I want to know what is the correct open chain form for this molecule? And as I've said, I have asked this question before on an exam, and people got it wrong. And then I asked it again on a final exam in a slightly modified form, and people still got it wrong, knowing that they had got it wrong the first time and having worked on it. So this is kind of hard. The hard part is actually not the hemiacetal part. That part's pretty easy. The hard part is getting all the stereochemistry straight. So I want to take you through that in a way I haven't done for previous sections of the class. This is like the first time I've walked through this in a lot of detail. Well, today with the 9 o'clock class and then you guys. So let's start where we started above. Let's start with the nucleophile, and we'll number 1, 2, 3, 4, 5, and 6. Okay? 6 is going to be our carbonyl carbon, and it's going to be an aldehyde. And 1 is going to be the alcohol nucleophile. So I'm just going to draw OH here. 1, let's see, 2, 3, 4, 5, 6. All right, so there's the aldehyde, and I just want to make sure we did this right, so I'm going to number things. 4, 5, 6. We good? There's the OH group, there's the carbonyl carbon, there is the carbonyl oxygen. Do you see how we got there? That part, it should get so that that part's easy. Yes?
So the O within the ring is OH.
That's right. The O within the ring in the cyclic hemiacetal becomes the alcohol nucleophile in the open chain form. Good. All right, now what about the rest of the molecule? If you're following along, carbon 2 has a CH2OH group on it. Carbon 3 has an OH group. Carbon 4 has an OH group. Carbon 5 has an OH group. And those are all stereocenters. Now here's the key. Those stereocenters are not involved in the reaction. They have to be the same over here as they are over here. The only thing that changes in this reaction is we go from hemiacetal to aldehyde. So part of your task, and this is really a test of how much you mastered 351, because part of your task is molecule visualization in 3 dimensions and getting stereochemistry right. Not to put too fine a point at this, but people suck at this, and it takes practice, all right? So we're gonna do that. I actually learned something from the way I tried to explain it in the 9 a.m. hour. So you're getting the beta tested, refined version, which will hopefully go a little bit more smoothly. It turns out that it is easier to do this if you will, instead of, you can start with the chair form, but then if you redraw the chair form as though you were looking down on the molecule from above. So this is what I'm talking about, 3D visualization, and we're gonna need our Newman projection eyeball, which, since you guys are tired, and since I am an evil Sith Lord, is gonna be our yellow Anakin, I hate you eyes. So yes, if you need to stare at me and shout I hate you while I tell you I have the high ground, that's fine, go for it. You underestimate my power. We will see, won't we? All right, so here is a 6-membered ring with an oxygen. We're drawing the sugar from above. You should be able to do this from 351. Briefly, axial and equatorial up positions will be wedges. Axial and equatorial down positions will be dashes. So the OH group, I'll just number around the ring like we've done in the drawing above. The OH group on blue 6 should be a wedge or a dash. Come on, you better know that. Good. Okay, 5 should be a dash for similar reasons. 4 should be a wedge. Let's see, 3 should be a dash, and then the CH2OH group on carbon 2 is an equatorial up position, so that makes it a wedge. I found it most convenient to draw the molecule like that. If you want to and not draw the CH2OH and just draw a line like that, that's fine. Now, I found it useful to do the ring opening while drawing the molecule in exactly the same way. Just to review, hemiacetal opening, this is our OR group. This is going to become the carbonyl oxygen. This is the carbonyl carbon. So you're going to redraw the molecule in exactly the same way. Keep everything exactly where it is, only carbon 6 becomes an aldehyde, blue carbon 6. What used to be the hemiacetal OH group becomes the carbonyl oxygen, and everything else stays where it was. Unchanged, because it wasn't involved in the reaction. Now, we have the task of translating what we've got here into the correct stereochemistry in the way we've chosen to draw the molecule up here. There's multiple ways to do this, and it doesn't matter how you do it if you get it right 100% of the time. So one strategy, which I don't know that I recommend, is to assign R versus S at each and every stereocenter in the molecule, and then just make sure you also get it right up here. That will work. It is slow. And it assumes that you never make a mistake on R versus S. The challenge with R versus S here, as you can see pretty quickly, if we just try to do that for carbon 4, O is definitely the highest priority group, and the proton there is lower priority for sure. I'm going to erase it. But how about these 2 carbons? They're both carbons. So now you got to do tiebreaker. Well, what are they both bonded to? Well, they're both bonded to 2 carbons and an oxygen. I got to go out another atom. So it gets exhausting, and the more tiebreaking you do, the odds are that you're going to make a mistake. So there's actually an easier way. You can do the R versus S if you always get it right and you trust your process. More power to you. Here's maybe an easier way. Starting looking at carbon 5, we're going to make a distinction between carbons that are drawn at valleys versus carbons that are drawn at peaks. Do you know the ringtone for my mother when she calls me is the Death Star alarm, because I figure I need to respond when my mom calls. And the ringtone when my dad calls is, guess what?
I am your father.
I am your father, yes, very good. Not a very hard guess, was it? My sister is Jabba the Hutt saying Boshuda, but I don't know if she's offended by that or not. Okay, so carbon 5 is at a valley, 6 is on the right, 4 is on the left, and when carbon 5 is at a valley with 6 on the left, right, and 4 on the left, the OH is a wedge. Come up here to my drawing here, 6 is still on the right, and 4 is still on the left, but carbon 5 is at a peak, not a valley. To keep the stereochemical configuration the same, we would have had to swing that up, and now the OH group that used to be a dash should now be what? A wedge, so you switch it. It's that easy, okay? Do that for carbon 4 from our perspective, and we do kind of have to tilt our heads a little bit. Looking straight on at carbon 4, 5 is on the right, 3 is on the left, 4 is at a valley, and the OH is a wedge. We got that same situation here. Do you see it? 5's on the right, 3's on the left, 4 is at a valley. The OH group should similarly be a wedge. Yes?
Why is the first OH a wedge?
You're talking about this one?
Yeah.
It has to be. It is a dash here, but the only reason it's a dash is because 5 is at a valley instead of a peak. So to get from here to here, we had to basically flip that carbon over. Okay, similarly with carbon 3, you sort of have to rotate yourself around and look at carbon 3. If we're standing over here, looking at carbon 3 from that direction, 4 would be on our right, 2 would be on our left, and 3 would be at what, a valley or a peak? Valley, right? So when 3 is at a valley with 4 on our right and 2 on our left, the OH is a dash. Coming up here, that switches, right? 4 is still on our right, 2 is still on our left, but 3 is at a peak. So the OH group on carbon 3 must be a dash. Lastly, carbon 2. This one's kind of troubling. Looking at our perspective, let's see. What should it be? Okay, let's, from our perspective looking at it here, just looking at it straight on, 1 is on our right, 3 is on our left, 2 is at a peak, and the CH2OH group is a wedge. Up here, notice the switch, 1 is on our left now. 3 is on our right, but 2 is also on a valley, right? So it stays a wedge. You can get to that simply by steering the molecule, doing a steering wheel action to turn the molecule around. Yes?
If you were to like flip the whole thing, they were all dashes, would that work as well? So like
If you pancake flip the whole molecule and they're all dashes, that's right too. You just have to, on a multiple choice exam though, you're going to have to pick the answer that's right, that's drawn the way I choose to draw it, which may not originally be the way you choose to draw it. Yeah. Yes?
So, is it okay if we start with 5 being down and also a wedge? Like, is that like functionally the same?
Is it okay if you, the question is, I'm going to only redraw part of the molecule. If you drew it like this, with 6 on the right and 4 on the left, and 5 being at a valley, no, that stereo center would have to be a wedge. Okay, one last thing. The often people don't like to continue drawing this CH2OH group like that. They like to draw the longest carbon chain as a completely flat zigzag. So one of the things people will do is they're going to take that OH group on carbon 2 that's pointing out at you, and they're going to rotate it around and put it in the plane of the page. So here's let me just draw the hydrogen that's implied but not shown there. And we'll redraw the whole molecule in the way we've drawn it so far. OH here, OH there. I'm not going to renumber it. You can see that by analogy. Here's carbon, fine, 6, 5, 4, 3, 2, 1. We're going to put the CH2OH group here. And now we got to figure out what happens to this alcohol. If we swing this carbon around to put it in the plane of the page, that's going to bring the proton up as a wedge, and that will put the OH group 1 down as a dash. Okay, so that's how you go through it, and it's worth some practice to see if you can do it. Go ahead.
Yeah, so the only reason why that alcohol doesn't attack the organic carbon is because it forms a seven member.
Good question. So you just noticed that this OH group here is, let's count, 1, 2, 3, 4, 5, 6, 7 atoms away from the carbonyl carbon. And you're asking, why doesn't that act as a nucleophile to make a 7-membered ring? That probably happens. The answer to your question really gets to something that we talk about in detail in Chemistry 552, which is, nobody takes it unless they have to, but you're all invited to. My colleague Dennis teaches it, and they talk about relative stability of rings. You learned some of this in 351. A 7-membered ring is a little bit less stable than a 6-membered ring. And a 5-membered ring is also a little bit less stable than a 6-membered ring because of ring strain and some other issues. So 6 is really a sweet spot, and that's why it's favored over the 7-membered ring. You could also ask, if you did this OH group as an alternative, that would make a 5-membered ring. Why doesn't that happen? Well, it can, and under certain circumstances, you can actually make that happen, but it's not the most stable option. Yep. Good. Other questions? I see another hand out there. Yeah.
Sorry, I know this is back a little bit, but could we go over carbon number 4 one more time, please?
Carbon number 4, yeah. So just zooming in on that, 5 is on our right. We're sort of standing looking at it from the side, so tilt your head if you have to. 5 is on our right, 3 is on our left, 4 is at a valley, and OH is a wedge. In our drawing up here, we got exactly the same situation. 5's on our right, 3's on our left, 4's at a valley, so it's still a wedge. Yep, now what I've told you is a little bit less technical than doing the R or the S, but it gets you to the same answer, maybe a little bit faster. Yeah?
One thing that also came to mind, building the model for it and then just straightening it out.
Yeah, so building the model for it and straightening it out. I definitely recommend that as practice, though you need to put in the practice ahead of time, because my sense is that in the testing center, with the limited amount of space they give you, a whole box of little balls that roll around is suddenly very stressful, and you run the risk of having a comedy routine going on amid the fog of war. The other thing I would say is, if you don't practice, I've had students that build the model and still get it wrong, so you got to build the model right to get the right answer. So yeah. Let me give you something to practice on to test yourself how well you're doing this. Okay, just a second. I'm going to give you the example, then I will answer your question. Shoot. I want to draw an axial OH group on this carbon in the front. So to do that, you have to know that this bond in the back is just behind the bond that's in the front. You get it? Okay, so this one happens to, well, I won't tell you what it's called, because if I do, you could just Google what the open chain form is and say that you won. Don't do that because, of course, you don't have Google on the exam. But go ahead and draw for me, not now, but afterwards, what the open chain form is. And I'll go ahead and put the answer in the notes. Or rather, what's actually going to happen is I'm going to forget to put the answer in the notes, and one of you is going to email me, and then I'm going to upload updated notes. So just so we're all sure about how this is going to go down. Draw the open chain form of that carbohydrate. That will be good practice. Okay, now I missed a question. Yeah, go ahead.
Going back to the top six, the molecule on the top right, shouldn't there be like a methyl oxygen group?
Yeah, the CH2OH group here is this carbon here. We've just straightened it out a little bit.
Oh.
Yep.
Okay.
That's all. Yep. Okay, others? Did I see somebody?
It's just not stable configuration.
Go back where?
So we can see the practice problem again.
No, sorry, that was your only view of it. No, there it is. Sad. Do you want to know the first interaction of my oldest son with my second son when we brought him home from the hospital was that Nate clocked baby Jack in the head with a fire truck. And immediately, because you just don't know what to do when you're a first son. It's not that we had ever clocked Nate in the head with fire trucks before. I'm not sure where he learned that, but maybe there's some weird self-preservation instinct. Anyway, yeah, he was immediately remorseful. We said, Natey, what's wrong? And he said, baby Jack, fire truck, sad. So anyway, so when you said sad, I suddenly was 20 years ago and Nate and Jack in the fire truck. I don't know what the lesson is. Go ahead.
Because this entire process makes rings and multiple rings, is there a certain length of chain that this primarily works for? Does it work for anything?
Yeah, it's a good question. Is there a length of chain that this works for? 5 and 6 membered rings are the most stable. If you go, sorry, some of you are still. If you go to 4 membered rings, they're possible but more strained. 3 membered rings also possible but even more strained. As you start to get bigger than 7, what happens is the tether between the nucleophile and the electrophile gets long enough that it stops making much of a difference in how fast they can find each other. Yeah. So it's actually an interesting field. The field of making rings is called macrocyclization, and it's actually still involved. We do some things in my lab that are related to it, but on much larger molecules. So it's kind of fun. But for now, if you remember that the sweet spot is a 6-membered ring and 5-membered rings, good, but just a little less, that's good enough. Yep. Okay. Well, okay. You will make in this class. You'll probably learn other reactions that make 4 and 3-membered rings too. But for now, for hemiacetals, 5 and 6 is the sweet spot. Okay. Others? Yes. Oh. Do we need to know how to go from the open chain form back to a ring? I don't think I've asked the question in that format before, though I could, and it would involve basically the same principles. And now you're going to go into witness protection, right? No, I mean, what you would do is essentially say, that would be difficult for this problem because, as I've told you, the other ring sizes are a possibility. So, but if I told you what size ring to make, you could figure it out. And then getting the stereochemistry right would be exactly the same process. All right. Let's see. So now, as I mentioned, we didn't get quite as far as we needed to in chapter 14 today. So you need to take a breath and get ready for the fire hose. It won't be too bad because we're not going to talk about a lot of these reactions in too much detail. One that you need to be aware of, but that is not hard at all, is called hydrate formation. This is basically exactly the same as acetal formation, only the nucleophile is water. And you end up with a carbon that's bonded, a carbonyl carbon that's bonded to 2 OH groups. You can do this with aldehydes or ketones, And it turns out that you can do this under both acidic and basic conditions. So acid catalyzed works just fine. Under acid catalyzed conditions, I won't draw the mechanism because you've basically seen it before. For acetal formation, you would expect the carbonyl oxygen to be protonated by the acid, in this case H3O plus first, to generate an oxonium ion, and then water would attack as the nucleophile to give you, and then a proton transfer would occur to regenerate your acid, and you would get this product, which is called a hydrate. If it's from an aldehyde, it's called an aldehyde hydrate. If it's from a ketone, it's called a ketone hydrate. Similar thing here. Sorry, I guess we could label one of the oxygens because it was the nucleophile purple. Carbonyl carbon, carbonyl oxygen, same thing with the ketone, right? This happens also under basic conditions. Those are okay as well. And the reason is that OH minus is a good enough nucleophile to attack a carbonyl carbon directly to get a negatively charged tetrahedral intermediate. So what you would expect under basic conditions is that the OH minus attacks the carbonyl carbon to get a tetrahedral intermediate, and then water protonates the oxygen in a second step. I'm not showing that in class. It should be in your text, and you should be able to figure it out from the stuff that we've talked about previously. We don't have a huge amount of time to delve into that. One interesting thing about hydrates is they tend to form with aldehydes and ketones to some extent anytime water's around, but the amount of hydrate that forms depends on how electrophilic the carbonyl carbon is. These are equilibrium processes, and there's going to be some percent, X percent hydrate versus Y percent aldehyde form for any given aldehyde or ketone. And you can use actually the percent hydrate formed as a measure for how electrophilic the carbonyl carbon is to begin with. So there's a question on your problem set. What percent hydrate should be greatest for these various carbonyl compounds? That's really just a question about which carbonyl compound is most electrophilic or electron poor. The more electrophilic the carbonyl carbon is, the better the reaction is where water acts as a nucleophile. Now, the last thing we need to do today, and then I'll tell you what we're delaying to next time, is something called cyanohydrin formation. This involves starting with an aldehyde or a ketone and using CN minus as a nucleophile and then some acid. Your text says HCl. That's probably not what most people do in practice because HCl can protonate CN minus. You make HCN gas, which is poisonous, and if you smell the almonds, you're already dead. So in practice, we tend to use a proton source that is much less acidic. Your text doesn't delve into that, so neither will I. And for right now, if you use HCl, that's just fine, because none of you are going to go in the lab immediately and try this. If you are going to do that, please come talk to an actual chemist first. And don't do it in your house, do it in the actual chemistry office. Not office, but in our labs upstairs. We'll talk about it, all right? Anyway, how does this work? Your text shows a mechanism that's, but I will show you something that's based on what we did for imine formation. Likely what has to happen is CN minus, which is a good nucleophile, attacks the carbonyl carbon at the same time as the carbon-oxygen pi bond is breaking, at the same time as we're picking up a proton from the acid. This is basically what we did for imine formation. You should be able to see the relationship between what we've done so far. Carbonyl carbon, carbonyl oxygen is now the OH group, and then here's the nucleophile. The reason your text does this is that cyanohydrins themselves are useful later on in chapter 16. We will learn that you can use a strong acid and heat to convert the CN minus into a carboxylic acid group. And that's a useful product. So we're introducing cyanohydrin formation at this stage so that we can do some other interesting things later on. What we didn't get to today are two important subjects which I want you to read about in the study guide. Wittig reaction is an important one, and then the other one is reductive amination. And once we deal with those two topics, it'll probably take us 10 minutes to do that on Monday, then we'll move on to chapter 15. Okay, have a great weekend. See you Monday.